This is Calculus 2 class. We're gonna study Taylor and Maclaurin series. Previous session, when we have power series, we find the function which represent the power series. That one good example is geometric series. Geometric series represent rational function 1 over 1 minus x. This session, we study reverse way. If given the function, how can I find the power series? Let's begin this session. Let's start Taylor series. Before we talking about Taylor series, let's start with the power series. The power series is defined an x minus cn n equals 0 to infinity. So center is c, coefficient an. Now we know the function of f of x. That's gonna be a given function. We know the some function sine, cosine, exponential log. How gonna find power series? What is the power series represent this function? So c is given, center is given, then we have to find an. What is an gonna be? What is an gonna be? Here is where we start. We know the f of x. We're gonna find an coefficient. Before we start to find an, let's expand this power series a0, a1, x minus c, a2, x minus c squared, a cube, x minus c cube, an, x minus cn. So let's just start to find a0 first. First, you want to find a0. You plug in x equals c. You're going to see what's going on here. When we plug in the f of c, we know this value because we know the function of f of x. Right side, you plug in each term right there, a0 plus c minus c is 0. Next term is 0. Everything 0 except a0. So you find a0 coefficient gonna be f of c. Okay? Let's do second. You wanna find a1. So you're gonna take a derivative of a prime x, left side. Right side is a1, a2, 2x minus c, a3 times 3x minus c squared. So you plug in the c here. You plug in the c there. F prime c gonna be a1. So you find a1. That's f prime c. Let's do one more. Second derivative x, a2 times 2, 2a2 plus 3a3 times 2 x minus c plus something like that. So what do you have here? F second derivative of c, 2a2. Now a2 gonna be f second derivative c over 2. So previous slides, we find a0, a1, a2. Let's find a3. So we're going to take a derivative, both sides, one more time. Third derivative, you write this rotation. Third derivative, 3 times 2, a3. 4 times 3 times 2, a4. X minus c plus 5 times 4 times 3, a5, x minus c squared. So we plug in x equals 0 one more time here. F third derivative c, 3 times 2, 3 times 2a, 3, everything else is 0. you find A3 gonna be F third derivative C 3 times 2. 3 times 2 times 1 is a factorial 3. Factorial F3C. Can you see the pattern yet? So let's do one more time. Fourth derivative, X. You see 4 times 3 times 2, A4 plus 4 times 5 times 4 times 3 times 2, A5 X minus C. So you find F4's derivative of C gonna be 4 times 3 times 2, A4. So you see A4 gonna be F4 derivative of C, 4 times 3 times 2 times 1, F4C, 4 factorial. Can you see the pattern, guys, here? First one is A0 is F of 0. A1 is F prime C. A2 gonna be F second derivative with C. This one is another way you put the factorial. 2 times 1 is 2 factorial. A3 gonna be F third derivative C, 3 factorial. F4 is gonna be fourth derivative of C, 4 factorial. So I'm pretty sure you guys get the idea. An gonna be, what's the derivative? Fn's derivative, C n factorial. So fx gonna be now, you see, fx, given function fx, you write the power series, an gonna be fn's derivative c over n factorial x minus c n power n equals 0 to infinity. That's we call, this one is we call Taylor series. Okay, so I'm going to introduce what the Taylor series look like. We prove the Taylor series if, first one is, you see, if give the f of x right there, you can write the f of x as the power series. This one is an. So how can find the an? And derivative, you plug in the center divided by n factorial. So when you expand the Taylor series f of c, f prime c over 1 factorial x minus c, f second derivative c divided by 2 factorial, so on. We call this one is Taylor series. Taylor series. Center is 0. What is the most important thing is, here is you cannot forget f is derivative at the c, which means f can be differentiable at c, okay? So we're gonna have more specific example later. Another one is center is 0, more simpler one. Center is 0, c gonna be 0, looks like here, f of x, summation n equals 0 to infinity fn of 0 over n factorial xn. Then you're going to expand the form f of 0, f prime of 0 over 1 factorial x, f second derivative of 0 over 2 factorial, so on. We call this one is Maclaurin series. Maclaurin series meaning it's sometimes 0 for Taylor series. So you guys, I think you guys curious about how gonna we use Taylor or Maclaurin series. So this one is we use approximate function with the polynomial. I give the more specific example later. Approximate polynomial help analyze behavior function near the sum point and basis for numerical method or solving different equation you guys taking next semester. Here is the one example to find Maclaurin series for the function. So series gonna be, we wanna find Maclaurin series. First thing is you're gonna have, that's gonna be center is 0, c gonna be 0. So they give function f of x. So f of x gonna be summation Maclaurin series n equals 0 to infinity fn's derivative of 0 over n factorial xn. That's you're gonna find it. Another way you're gonna write it 1 plus, no, not 1 guys. How can I write it? F of 0, f first derivative over 1 factorial x, second derivative 0, 2 factorial x squared, third derivative 0, 3 factorial x cubed. Okay, let's find the first coefficient. So f of x equal e to the x, f prime x, e to the x, f second derivative x, e to the x, f nth derivative, of course, e to the x. From there, guys, from there, f of 0 equal e to the 0 is 1. F prime 0 gonna be e to the 0 equal 1. F second derivative 0 is e to the 0 equal 1. F nth derivative 0 gonna be e to the 0 equal 1. So what do you have this Maclaurin series for e to the x? F of 0 is 1. First derivative of 0 is 1. Second derivative 0 is 1. Third derivative of 0 is 1. So conclusion is e to the x function. Maclaurin series is gonna be n to 0 to infinity, 1 over n factorial xn. Okay, so you guys try to find radius conversion, interval of conversions for this exponential function. Then you're gonna find this one is gonna be all real number. This Maclaurin series converges. Let's have another example for Maclaurin series for fx is cosine x, right? So let's start. We know that f of x gonna be looks like summation n equals 0 to infinity fn 0 over m factorial xn. That's the Maclaurin series, right? So function is this time is f of x cosine x. So f of x cosine x, f prime x, negative sine x, f second derivative gonna be negative cosine x, f third derivative gonna be sine x. Then go back, right? So this one is fourth derivative x. This one is fifth derivative of x. This one is sixth derivative x. This one is seventh derivative x. I think you get the idea. So find the coefficient. F of 0 is 1. F prime 0 is 0. F second derivative of 0 is negative 1. For third derivative 0 gonna be 0. This also F fourth derivative 0. This one is a fifth derivative 0. This one is a sixth derivative 0. This one is a seventh derivative 0, right? So now find the Maclaurin series for cosine. So cosine x gonna be, expand this form first. So f of 0, f prime 0, x. F second derivative 0 is x squared over 2 factorial. F third derivative 0 over 3 factorial x cubed. Fourth derivative 0, 4 factorial x fourth power. Okay, let's do f of 0. This value is 1. This value is 0. This value gonna be negative 1. This is 0. fourth derivative 1. So cosine x gonna be 1 minus 1 over 2 factorial x squared, 1 over 4 factorial x fourth power, minus 1 over 6 factorial x6. Summation notation, summation n equals 0 to infinity, alternating sign, negative 1 and n. Bottom is, here is gonna be, bottom is nothing. 2 factorial and 4n factorial, 6n factorial, right? 2n factorial, n equals 0 is 0 factorial 1. So that's I 2n factorial x 2n. That you find Maclaurin series for cosine. Another example for Maclaurin series, f of x sine x, okay? So let's just start this one, guys. All right? So form of Maclaurin series, the center is 0. Let's keep in mind. Here is going to be f of x. F of x going to be Maclaurin series, going to be summation n equals 0 to infinity fn's derivative 0 and factorial xn. Okay, sine function is differentiable everywhere. So let's find f of x, sine x, f first derivative gonna be cosine x, second derivative gonna be negative sine x because cosine, derivative cosine is negative sine x, third derivative gonna be negative cosine x, fourth derivative is sine x. This one is gonna be fourth derivative x. This one is fifth derivative x. This one is the sixth derivative x. This one is seventh derivative x. That's repeated, right, guys? So next one is we want to find, now we want to find what is f of 0 is, sine 0 is 0. F first derivative of 0, cosine 0 is 1, sine 0 is 0, cosine 0 is 1, but here is a negative, negative 1. So another thing is the same thing is repeated. Cycle every fourth multiplier. Okay? Now, let's find f of x. F of x. F of x. F of 0. F prime 0x. Second derivative 0 to factorial x squared. Third derivative 0 over 3 factorial fourth x over fourth derivative 4 factorial x fourth. Here is x cubed. Let's plug in one by one, guys. Here is f of x is sine x. Here is gonna be f of 0. F of 0 is gonna be 0. So this one is a 0. F prime 0 gonna be 1. So x, f second derivative 0. Third derivative gonna be 1 negative 1 over 3 factorial x cubed. Fourth derivative 0. Next one is gonna be fourth derivative gonna be 0. Fifth derivative 1. Like that. See the pattern? How can I write the general term this one, guys? This one, summation, alternating series, negative 1 and n, positive. And it's just start to what? Guys, just start n equals 0 to infinity. Bottom is, first one is 1. So 2n plus 1 factorial x 2n plus 1. That's the Maclaurin series for the sine. Previous example, we find Maclaurin series by using the definition. Now, so it's a lot of work to find the Maclaurin series or Taylor series later, but how gonna find the series quickly? One idea is we're gonna find a new Taylor Maclaurin series from old one. Old one we already knew. So let's just start this one. We find the Maclaurin series about e to the x, cosine x, ln x. Ln is we did from the power series, geometry power series. We're gonna use each Maclaurin or geometry power series to find a new one. Let's try first one. Say gonna be fx is x squared e to the x. I wanna use e to the x first. So e to the x, say there is e to the x gonna be n equals 0 to infinity. Here, 1 over n factorial xn. So from here, we can find e to the 2x. How can find e to the 2x? You replace x with the 2x, right? Summation n equals 0 to infinity 1 over n factorial 2xn. So distribute n into the power summation n equals 0 to infinity 2n m factorial xn. So you find e to the x. You find the Maclaurin series for e to the 2x easily. Now, we are looking for f of x right here, guys. F of x gonna be x squared times e to the 2x. So we have x squared, but we know the Maclaurin series of this, right? So x squared times the summation n equals 0 to infinity 2n m factorial xn. Can you simplify this? Yes, this one is summation n equals 0 to infinity 2n m factorial. You have x squared here, you have xn here. Power is you're gonna add x n plus 2. That's gonna be Maclaurin series. The fx is x squared times e to the 2x. Everybody understand? So from this example, we notice we don't have to do Maclaurin series from scratch, find a new one. If you can use old one, that's great because we save our time. So let's try to B, guys. B is, you can see B gonna be, can you see this one is, you see cosine x, right? So cosine x, Maclaurin series for cosine x, summation n equals 0 to infinity, negative 1 and n, 2m factorial x to n. But we want to find f of x, cosine square root of x. So what do you have to do? You're going to replace x with the square root of x. That's all you need to find the Maclaurin series for this. So let's find it. Summation n equals 0 to infinity, negative 1 and n, 2n factorial x is replaced with the square root of x, 2n. So what do you have this simplification, this one, right? Square root x square is x. So this one gonna be summation n equals 0 to infinity, negative 1 and n, 2n factorial xn. That's the Maclaurin series for cosine square root of x. Let's do the C. So we want to find the Maclaurin series for ln 1 minus x, right? So we already find ln 1 plus x from the geometric power series. So what Now, here is ln 1 plus x gonna be, we find the previous session, summation n equals 0 to infinity, -1 n xn plus 1 n plus 1. That's you find it. Now, how gonna find ln 1 minus x? This one is ln 1 minus x. Here, ln 1 plus minus x. So this one gonna be replace x with negative x. So you have this one is a summation n equals 0 to infinity -1 and n negative x n plus 1 over n plus 1. Right? So now let's simplify this one. Let's do this part, guys. This part. So I can write it -1 n plus 1 times x n plus 1. So you have summation n equals 0 to infinity -1 and n -1 and n plus 1 x n plus 1 over n plus 1. Now look at this one, n plus 1 together, -1 n times -1 n plus 1, -1 2n plus 1. What is this number? Odd number, odd power, -1 3, -1 5. That meaning is always -1, okay? So here you have summation n equals 0 to infinity -1 over n plus 1 x n plus 1. That's the Maclaurin series for ln 1 minus n. Now you have question about how we can get the fundamental Maclaurin series for each function. I gonna provide you. You can use the table of Maclaurin series to find new Maclaurin series. So now, previous one, they give the function, we find the Maclaurin series. Now, what you have to do, guys, we have power series, we have Maclaurin series. Clearly see all the Maclaurin series right here. Then we're gonna find function which represent this power series. So we quite reverse way to find the function. Okay, first one. Here this idea is, guys, this one is we coming from the table of power series. Best way you print out the table of powers Maclaurin series to use it when you solve this kind of problem. You can find that one on the blackboard, guys, okay? So I'm gonna give 3 Maclaurin series for this question, okay? So I'm gonna put here, first one is e to the x, using this one, e to the x gonna be summation n equals 0 to infinity 1 over n factorial xn. Okay, second is ln 1 plus x gonna be summation n equals 0 to infinity -1 and n x n plus 1 over n plus 1. Third one is cosine x summation n equals 0 to infinity -1 and n 2n factorial x to n. So we're gonna using this fundamental Maclaurin series find the function, guys. Here is a find the function. What this Maclaurin series represent? That we have find it, guys. So what is key idea is look at the coefficient. That's the very important. Look at the coefficient, especially denominator. Denominator cannot be changed, guys. Okay, denominator cannot be changed. So you each check the denominator, then you figure it out the candidate for the function. So n factorial is right here. So you're gonna write this first one. A gonna be summation n equals 0 to infinity m factorial, nothing there. So you're gonna have put together here. Power is n. You put together everything. -1 to x n. Same thing, this one, right? This one. So this one is a summation n equals 0 to infinity, -1 times 2 times x, -2x, and m factorial. What this power series represent? E to the -2x. So that's where you're going to find the function which represents this Maclaurin series. Everything make sense? So let's try to be now. M plus 1. Where is M plus 1, guys? Here is M plus 1 is right here. ln, right? Summation n equals 0 to infinity, -1 and n, m plus 1. That's the here. Coefficient right there, -1 and n, m plus 1. Now, which part we take care of here? You take care of 3n plus 2 x n plus 1. So same power, you separate n plus 3 times 3n plus 1 times x n plus 1. That's what we're going to do here. 3 times 3x n plus 1. Okay, that's what we're going to do it. All right. Then how I'm going to rewrite this one is a summation n equals 0 to infinity. So bottom is n plus 1. Here is 3 times -1 power, 3 times -1 and n. Here is 3x n plus 1. See, same form. So -1 and n, x n plus 1, extra number is 3, 3. Summation n equals 0 to infinity, -1 and n plus 1 times 3x n plus 1. This one represents 3 times this one. Only this term represents ln function. ln 1 plus, not x, 3x, 3x. That's we find the function which represents this power series. Let's have another example. Last one is summation n equals 0 to infinity -1 and an xn. I say check the denominator. Here is 2n factorial is right here. That's gonna be we should use cosine. So let's try to this form. Keep in mind this form here. Then you're gonna see summation n equals 0 to infinity, -1 and n, x 4n. Here is 2n factorial. Good candidate cosine f, but here's a 2n. You have to that form right here. Summation n equals 0 to infinity. Everything looks same except that part. So I need 2n. What is inside gonna be? Look at this one is a 4n. We only need 2n. The inside gonna be x squared. 2 times 2n is 4n. Now you find it. Summation n equals 0 to infinity, -1 and n, 2n factorial, x squared. Here is x, x2n. Here is x squared gonna be cosine. Cosine, I'm sorry, not this way, guys. Here is x squared, 2n. So we're gonna be cosine. That's gonna be cosine x squared. So now we find Maclaurin series cosine x squared. So now you have idea, right? So you guys print out the table of fundamental Maclaurin series. You freely use the table to find the new Maclaurin series for the given function. Previous example, whenever you have the Maclaurin series and find the function for Maclaurin series. Now, we want to find sum of series. Previous session, when you do the series test, we couldn't find sum of all the series, which is convergent. We only know that series is going to be convergent divergent. But however, if you use Maclaurin series for the sum function, we can find the sum of a series. So let's just start with the first one, okay? So first we have figured it out. This power series represent which function? That's the first step you have taken. So how do you know? I explained previous slides. We're gonna see the denominator. Okay, denominator n plus 1, here's n plus 1. So we're going to use ln function. So what you want to do this one is a gonna be, keep in mind that that's going to represent ln function. So negative 1 and n, same thing is negative 1 and n2. So this one is n plus 1 times right here, guys, 1 over 2n. Another way you write it, n equals 0 to infinity, negative 1 and n plus 1 times 1 over 2n. This should be x part. So we have this one equal ln 1 plus 1 over 2. What is 1 plus 1 over 2, guys? This value gonna be ln 3 over 2. So this power series, some of this power series gonna be ln 3 over 2. Is that cool to find the sum of power series, right? Let's go second, B part. So first you check it out, denominator. Denominator n factorial, here is n factorial. Numerator gonna be 1. So here's very careful. Everything is inside the x, okay? So let's do this one. Summation n equals 0 to infinity. 1, n factorial, that's the only coefficient. Everything. 2n plus 1, negative 1n. But here's the power. Look at, check it out. Power is n. But here's n plus 1. Then 2n plus 1 is separate. 2 times 2n, negative n. So this one put together, 2 times negative 2n. Look at the e to the x form. 1 of n factorial xn. There is extra 2, you take it out. 2 summation n equals 0 to infinity 1 of n factorial negative 2n. Now you notice this one is x. Replace x with negative 2. So you have 2 times e negative 2. Some of this series gonna be, now you can tell about this one gonna be 2 e to the negative 2. So you find the sum of that series. Let's do the C, guys. If you can stop the video, do by yourself, guys, okay? So now you have checked denominator 2n plus 1 factorial. That's right here. That's candidate, good candidate to sin x. Top is negative 1n only. So negative 1n only. That's straightforward. 3 gonna be 3 have base 3. Power is 2n plus 1. That's very straightforward. 3, 2n plus 1. So this one is represent a sign. X gonna replace the 3. The sum of this series gonna be sine 3. So now we finish up the Taylor Maclaurin series. There is so many applications for this series. Guys, keep working on Taylor and Maclaurin series.